up with some problems. Let's start by graphing the parent function. What's that look like?
It's just coming up and using the x as a asymptote.
Well, using the y-axis as an asymptote.
Oh, okay. Y is the asymptote.
Right, but the equation of the y-axis is x equals 0.
Yeah.
Okay, and there is no horizontal asymptote here. It looks like there can be. When you see a lot of graphs, it looks like this could be flattening so fast that it's approaching a horizontal asymptote, but it does not. It goes on to infinity. Okay? Now, what I just graphed goes through this point, 1, 0. And now if I said, let's graph y equals log base 3 of x, well, guess that. That's going to be almost indistinguishable from our first graph. It still has to go through that same point. Whether it's below or above the other one, I don't even know right offhand. I think it's actually above. But the thing is if I gave you just the red curve or just the black curve, you wouldn't really be able to tell me much as to the base. You'd say that they're both the log function, but they could have different bases. And even the natural log, y equals natural log of x, it's still going to go through that same point. And again, I don't know if it's above the black or the red, and I don't really care at the moment. So that's how we graph the parent log functions. And each of these would be a parent function. In other words, that might be the parent function, that might be the parent function, or that might be the parent function. And then what we're looking at are transformations from the parent function. So let's look at the simplest one, common log. Now, if I said to you, you want me to go through the 6 transformations for this function?
Yeah.
What's that going to look like?
Reflection over the x.
Okay. What's this going to look like?
Reflection over the y. Stretch.
Vertical stretch, because there is a difference between vertical and horizontal stretches.
Horizontal shrink.
Good. Goes the opposite as the vertical. In other words, numbers greater than 1 are stretches, numbers greater than 1 here are shrinks, and vice versa. Numbers less than 1 here are shrinks, numbers less than 1 here are stretches. And finally,
translations. The translation band too.
no. Notice, first of all, well, you need to use the words horizontal or vertical.
Okay. That's a vertical translation.
Okay, that's called a vertical shift.
Okay.
Horizontal shifts are also called shifts. So I don't know that it's fair to call this a translation. All of these are translations. All 6 of them are translations. That is a vertical shift down. And finally, by how much and which way?
To the right 7.
Where is the new vertical asymptote for that function?
The new vertical asymptote is x equals 7.
Good. Looks like you know them all to me. Now, the one thing about logs is they happen to be the inverses of exponentials. And that can be a little confusing because they're also the equivalent of certain exponentials. But if you were to look at an exponential function like that, notice that that exponential function, which is y equal 10 to the x power, is the inverse of this function, y equal log base 10 of x. They're not equivalent. The equivalent of the upper one would be log base 10 of y equals x. These two are the same. But notice this is not the same as that second one. This is the inverse of the top one. And if you're ever wondering how a log function is going to graph, well, picture a reflection of an exponential function. Remember, inverses are reflections about what line?
Y equals x.
Yeah. In other words, there's always, when I'm talking about inverse functions, they're always going to be reflections over that line. All right, what else? Cole? What are your other weak subjects that you're going to be tested on? I don't know of any, so you're going to have to help me with that.
Probably logs in general.
Okay, let's talk about converting logs, compressing them, condensing them, expanding them. So give me the logarithmic expression that's equivalent to that.
Log base bx. Log base by equals x. So.
Always remember one thing about logs. They are exponents. So if I have no clue as to how to convert this, I start there. I know that the log of whatever is the exponent. So I know it's always x. Well, the b is relatively easy to figure out where that goes. There's only one place left for the y. Okay, so give me the logarithmic expression for that.
Log base 10 1,000 is equal to 3.
Log base 10 of 1,000 equals 3. Is that what you said?
Yep.
Okay. Now let's talk about, tell me some of these.
One.
What's that equal to?
1.
Is that equal to?
This I don't know.
guess. Your guess is going to be correct. In other words, those cancel pretty much.
Oh. Zero.
Expand.
Log of x plus log of y.
Expand that one.
Log of xy plus log of xy.
Got to think about that for a second. No, I don't think so. First of all, we're multiplying. Second, let's change this expression, first of all, to this. Now split it up.
Log x squared plus log y squared.
Now bring the exponents down. In other words, the third rule of logs allows you to do that.
Oh, so 2 log x plus 2 log y.
Okay. Now I'm going to change the problem just slightly. Hold on. To that.
So it'll be log x plus 2 log y.
Good. Okay. How about log of y times square root of x over z?
So it would be log of y minus log square root of x, plus log square root of x, sorry, minus log z.
Okay, and that can be expanded more. Turn that radical sign into an x.
Log x. How about that?
Okay. I don't know what number I need here yet. Tell me what the next step. I'll put a number in there and then I'll change it, but what's the next step?
If your log bases are the same, you can eliminate the logs.
You want to condense.
Condense.
In other words, this is going the other direction from expanding.
Okay.
What we just did was expand. This time we want to condense. And there's a good reason why we want to condense this. It's the only way to really solve it.
You get log of x squared minus x.
Now what?
Then you can say that 10 to the third is equal to x squared minus x.
Now you have a quadratic that you need to solve. That's it. X squared minus x minus 1,000. Okay? Now, just for the sake of argument, let's say that our quadratic came out to be this. It's instead of 1,000. Because I don't know how to factor 1,000 to produce that middle term. So I said I'm not sure what number I need over here yet. And I don't want to spend time trying to figure out what number is going to give me a quadratic that factors nicely. Let's assume this is the quadratic we got. Now what?
We can factor it into x minus 3x plus 2.
So what are my two x answers?
2, negative 3. Oh, negative 3 and negative 2, so.
Both of those valid?
You have to run them through to make sure, you know.
And you got to run them through that equation, not this one. They will not violate the domain of the second one, but they will violate the domain on the original one. This answer does. So x equal minus 2 is not an answer. Only x equal 3 would be a solution. Condense that into a single log expression. You don't have to do it all in one step. And in fact, I would advise not doing it all in one step. I would do it in multiple rows. What would be the first thing you'd want to do?
Those are the coefficients. So
Okay, so what's the next line?
log x squared minus log root y plus log, these are the sixth.
Yep. In other words, it's really, when we move that exponent over, it goes, got to put parentheses around the z squared.
Yeah.
Okay. Now you can do the final single expression.
The log of x squared over root y times z squared.
Z to the 6th go in the numerator or the denominator?
Denominator.
No. Because of that.
Oh.
In other words, it was being added. Those two are being added, so their arguments are going to be multiplied in the numerator.
Okay.
Anything that's being subtracted goes in the denominator.
Okay.
Let me think for a minute if I can come up with... You seem like you know logs pretty good, Cole.
Better than I remember of knowing them.
Well, you know all the key things to know, which is, you know, 7 to the log base 7 of x is x. Things like that. You know your expansion rules, you know your condensing rules, and you know how to solve a log equation. What kind of calculator do you have?
Yeah, I Inspire.
So you can do this directly, but don't do it directly. Give me the change of base formula.
It's...
In other words, give me a... No, this is a precise answer, actually, also. But use the change of base formula to give me a ratio of 2 logs.
It's log of 5 over log of 7.
Mm-hmm.
Okay.
And it doesn't matter which log you use. I can use common log, I can use natural log, I can use log base 17. I'm not sure why I would ever use log base 17, but I could. In other words, all three of those are the same ratios. You'll get the exact same decimal in a calculator doing common log, natural log, or log base 17.
All right.
I don't think you need that much more help on logs. Let's talk another subject that you think you might be weak at. How's your trig?
Well, I think my trig's fine.
Okay. How is your how would you solve that?
Get them down to the same base, so you'd reduce the 9 to 3 squared, so you'd have 3 to the 2x, and reduce the 27 to...
Pretty important, I think, this step right here.
Yeah.
Is to represent the 9 as 3 squared inside parentheses.
Yeah.
The parentheses matter sometimes. They don't always, but like in this case, I could get confused if I don't use the parentheses. So
Yeah.
now what's the next line?
You have 3 to the 2x is equal to 3 to the 6x minus 3. And then you can just set the exponents equal to each other and solve.
Mm-hmm. Okay. How about this problem? What kind of an equation is this? Is it an algebra equation?
I don't know.
It's not. It's an exponential equation. And what distinguishes the two is exponential equations have the variable in the exponent. There is no algebraic solution to this. But that's why they teach you logs, is for solving exponential equations. So how would I solve this?
Log base 7 of 4 equals equal to x.
All right, I'm not sure that's my favorite way. Equals what? In other words, what you really did was you took the log base 7 of both sides. And that left x directly over there. But now you still got to use the change of base formula, right? So it's the log of 4 divided by the log of 7. So it's still 2 steps. Let's go back. I'm not sure this is worth even mentioning, but it might be, because you can get in trouble if you're always having to take the log of this number, the log base of that number. Let's just always take natural log of both sides, or common log of both sides. The fact that it's now a log equation allows me to do what with the x?
I don't know.
Think expand. When you're expanding that, what are you going to do with the x?
Put it in front.
That's exactly what you do with it. Now, it's an algebra problem. And x is natural log of 4 divided by natural log of 7. So it's the same number of steps. It just looked easier to take the log base 7 because it appeared to give you the answer in one step, and I suppose it did in a way. In other words, yeah, the answer is log base 4 divided by log base 7. Excuse me, the answer is log base 7 of 4, which is what this answer is. That's log base 7 of 4. It's just that we don't tend to work with bases that are not, in other words, you're not going to run into very many problems that have that expression in them. It just doesn't happen. Not in calculus, not in higher math. In other words, I would make a suggestion to you that whenever you run into a problem like this, whenever you have to take the log of both sides, just always take the natural log of both sides.
Right.
And then treat that as a number. And that's a number, which is what they are. All right, Cole, I'm going to let you go. I got a 4 o'clock I got to run to, and I will talk to you next Monday at 3:30.
Hello?
Does that work? Cole? Well, somehow we lost audio. I'm not sure how, but
There we go.
okay. We lost audio for a second, right as I was saying goodbye. All right, I'll talk to you next Monday at 3:30.
All right, talk to you next Monday.